Hey everyone, and welcome. If you're getting ready for your GCSE physics exam, you are in exactly the right place. Today, we're going to totally break down the IV characteristics required practical. Let's get you ready to ace those questions. Okay, so let's just jump right in. The whole point of this entire investigation is to figure out a really basic question. Do all electrical bits and pieces follow the same rules? You know, when you plug them into a circuit, do they all act the same? Or does each one have its own kind of unique personality? Well, that's exactly what we're here to find out. So here's our game plan for this explainer. First, we'll look at why we even bother doing this test. Then we'll meet the key players, the components themselves. After that, we'll see how to build a perfect circuit. Then comes the really important bit, decoding the graphs. And finally, we'll wrap up by looking at how you can use all this to absolutely nail the exam questions. Right, section 1. So why do we test these components? Well, like I said, it's all about uncovering the unique personality of each part, how it reacts when you start pushing electricity through it. Now, the fancy term for this is investigating IV characteristics. And really, all that means is that we're looking at the relationship between two things: current, which gets the symbol I, and potential difference, which we call V. The whole experiment is about what happens to that current when we change the potential difference. All right, let's move on. It's time to meet the three main characters in our little circuit story. These are the components you absolutely have to know inside and out for your exam. But first, let's make sure we're totally clear on the two things we're measuring. First up, we've got current. Just think of this as the actual amount of electricity flowing through the component. The official definition, the one that will get you marks, is the rate of flow of electrical charge, and we measure it in amperes, or just amps for short. And then there's potential difference. You probably know this better as voltage, right? This is the push, the energy that's actually driving the current around the circuit. We measure this one in volts. So think about it. We're changing the push and measuring how that affects the flow. Simple as that. So, who are these three characters we're investigating? Well, first, you've got the resistor. It's your steady, reliable, totally predictable friend. Then you have the filament lamp, which is a bit more dramatic. It gets hot, and as we'll see, it kind of changes its mind about things. And finally, the diode, which basically acts like a bouncer at a club. It's a strictly one-way street for current. Okay, on to the fun part. Section 3 is all about actually building the circuit. Now listen up, because this is AQA required practical number 4, so knowing the method is absolutely crucial. The method itself is pretty straightforward, actually. You build your circuit, making sure your ammeter is in series in the main loop, and your voltmeter is in parallel across the component you're testing. You'll use a variable resistor to tweak the potential difference, and for each setting, you'll write down the readings from both meters. You just keep doing that to get a nice range of results. Oh, and for the diode, don't forget that last vital step. You physically have to reverse the connections to it and do it all again to see what happens. And you know this is a big deal. For marks in any science practical, we need to know our variables. So the independent variable, the one we are deliberately changing, is the potential difference. The dependent variable is a thing we're measuring to see what happens, and that's the current. And a really important control variable, especially for the resistor, is temperature. We have to try and keep it the same because, as you're about to see, temperature can change everything. Okay, deep breath. You've done the experiment, you've got a table full of numbers. Now for the bit that really matters, decoding those IV graphs. This is where you turn all that data into actual understanding and, more importantly, into exam marks. First up, let's look at our steady, predictable friend, the ohmic resistor. So what does its graph look like? Well, for a resistor at a constant temperature, you get this perfect, beautiful straight line that goes right through the origin. This tells us something huge. The relationship is directly proportional. The gradient, or the steepness, is constant, which means the resistance isn't changing at all. This component is a model citizen of the circuit world. It obeys Ohm's law perfectly. And that phrase right there, directly proportional, is pure gold for your exam answer. It means if you double the potential difference, you double the current. If you triple one, you triple the other. It's simple, it's predictable, and it's ohmic. Lock that phrase away. Right, let's move on to the filament lamp. And this is where things start to get a whole lot more interesting. So the graph for the lamp is definitely not a straight line. It's this S-shaped curve that starts off steep and then gets shallower and shallower. So what's that telling us? It's showing that as the potential difference and the current go up, the resistance is also increasing. This component does not obey Ohm's law. We call it a non-ohmic component. But why does it do that? Well, the physics behind it is actually really cool. As more and more current flows through that tiny little filament wire, it gets incredibly hot, glowing hot. All that heat energy makes the metal ions inside the wire just vibrate like crazy. And that makes it much, much harder for the electrons to get past. More collisions means it's tougher for the current to flow, which is just another way of saying the resistance has gone up. And that brings us to our final component, the diode, our one-way gate. The graph for a diode is just extreme. In one direction, which we call the reverse direction, you get basically nothing. No current flows because the resistance is massive, like a solid wall. But if you hook it up in the forward direction, something amazing happens. Not much happens at first, until the potential difference hits about 0.6 or 0.7 volts. And then, bam, the current suddenly shoots up. It's like a switch has been flipped and the floodgates have opened. Right, let's pull all of this together. Section 5 is all about taking this knowledge and using it to your advantage to absolutely nail those exam questions. Okay, you need to listen to this next bit very, very carefully. This sentence is taken word for word from the AQA specification. It's not just some random fact. It is a fundamental piece of physics they 100% expect you to know and be able to explain. You should probably memorize it. You know, this one practical is incredible because it ticks so many boxes for your examiners. AT 6 and 7 are all about your hands-on skills. Can you use the meters correctly and build the circuit? But those working scientifically skills, the WS ones, are just as important. Can you pick out the variables? And crucially, can you look at those graphs, see the patterns, and explain what they mean? That's what WS 3.5 is all about, and it's worth a lot of marks. So I'm going to leave you with a final thought to chew on. We've just seen that a diode has this really specific personality, right? It only lets current flow in one direction. So how could you use that very specific property to protect another, more sensitive component from getting damaged? Think about it. That's the kind of application question that really separates a good answer from a truly great one.